Hi folks. This section we're going to talk about chemistry at a distance. One of the questions that I used to wonder was, how in the world can scientists know the chemical composition of the sun? The sun is 93 million miles away. Never have we sent a probe to the sun, scooped out a little bit, and brought it back to planet Earth. But they're always talking about what's the chemicals in the sun, what chemicals make up the atmosphere of Jupiter. You've got a distant star a long way away, and we know what its chemical composition is. How the heck do you do that? Well, this whole section is on light, and as you can imagine, the answer has to do with light. If you had any object that is a hot solid. So when I say hot solid, I mean something like the filament of an old-fashioned light bulb. Or if you want to talk about having a bonfire in your, I'm trying to draw a bonfire in your backyard, those hot logs and hot embers are going to give you a complete rainbow. And this is sometimes called a continuous emission spectra. But that complete rainbow is going to contain all of the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet, without any gaps in between. If you take the hot body of the star, a hot star is not a solid, but the particles are so close together and their molecules are bumping into each other with such ferocity that it is going to produce a continuous spectrum, just like a hot solid. So hot solid by its own doesn't really tell us very much. But the other thing that's interesting is our star is hot and gives that continuous spectrum, but it's surrounded by an envelope of gas. And gases emit something unique. The things that gases emit are things that are called line emission spectra. Each element on the periodic table, when it gets hot in a gaseous state, not in a solid, but in a gaseous state, it is going to produce not the whole Roy G. Biv entire spectra. What it's going to produce instead are just a few unique colors. And these are just like a fingerprint. A scientist can look at these collection of lines and tell if an element is hydrogen or helium or mercury. And as you can see, look at this helium spectrum. This is a mercury spectrum. See that big green line right there and that big yellow? Mercury vapor has a tendency to be kind of greeny yellow. Hydrogen's got a strong red line, blue line, purple lines. To someone who knows what they're looking at, each element is as unique as each one of your children is unique. So what makes these lines? Well, that was a big mystery for 100 years or so. And then along came a very important scientist named Niels Bohr. Here's a picture of Niels Bohr and his wife kind of tootling along on a motorcycle. Niels Bohr lived in the early 1900s. And Niels Bohr, if Einstein had not existed, his name would have been a household name. He had the misfortune of working at the same time as Einstein. And so he kind of got less publicity than he was probably due. Very important astronomer, or excuse me, not astronomer, but physicist in the history of science. Here's what Niels Bohr figured out, trying to explain these spectral lines. He figured out that inside of any atom, as you know, there's protons and neutrons in the nucleus, and there are places where the electrons can be and places where the electrons cannot be. Now, prior to Niels Bohr, people thought there was a nucleus and then electrons kind of whirly-gigged all the way around wherever they wanted. Well, Bohr figured out, no, that's not true. An electron can be here, or here, or here, but nowhere in between. Now, for those of you who've had chemistry, I'm using an overly simplified version of electron energy levels. As you know, if you've had some chem, it's much more complicated, but this picture works for what we're doing today. So how do these line spectra get produced? Well, here's how it works. And this is how every single photon or piece of light is produced. And it works like this. You've got the nucleus, and then you have electrons that are just all happily hanging out on their energy levels. Well, each one of these energy levels corresponds to an amount of energy. Electrons that are living close to the nucleus have lower energy. Those electrons at a further away energy level have a little bit higher energy. And those electrons that are still further away have a much, much higher energy. So here's how this goes. If an atom is sitting there minding its own business and energy gets added, okay, we add energy to an atom, and there's ways you can do that by hitting it with light, electricity, or heat. So I've got my electron sitting here, happy as a clam, and maybe it gets hit with a photon of light. Well, it's sort of like you've got a billiard ball on a pool table, and you just hit it with another billiard ball, and this ball now has lots and lots and lots of energy and speed, and it goes whee, and it zips along. Well, this electron, when it gets hit with a photon of light or some electricity, which just means an electron in motion, or you get it really, really hot, this guy absorbs some of that energy. Well, if you're going to be on this energy level, you can only have a certain amount of energy. So if we add energy to this electron, it can't hang out there anymore. So what it does is it jumps, and it jumps to the next energy level that it has enough speed and energy to hang out on. Now, once that electron has jumped that high, a weird and crazy thing happens. It leaves a hole behind it. It was here, it's no longer here, and there's a hole. Nature hates empty energy levels deep inside of atoms. It's something called Hens rule or Hens Law. So when that electron jumps and it left a hole, that hole's not going to be empty for long. Something's going to fill it. Typically what fills it is another electron. And it can be this one or one of the others. So let's say an electron from the second energy level falls in to that empty hole. When it falls in, it emits energy because it's going from a high level to a low level. So it has to give off some energy. And it does that by emitting a specific photon of light. Not just any old photon, but one that is so specific it corresponds to one and only one line in that spectra. Well, as you can imagine, when this electron falls, it leaves a hole. So what happens to fill that hole? Well, another electron falls in and emits another photon of light. And the photon it emits corresponds to one and only one line in the light spectra of that element. Every single element on the periodic table is going to have a slightly different arrangement of how close or how far away these electron energy levels are. And that is what makes each one of these unique line spectra for each chemical. And so if you have something that contains lithium, it's only going to produce these colors. If you have something that contains neon, it's only going to produce these wavelengths. And as I mentioned, these are very much like a fingerprint, unique to every individual element and chemical. So if you're talking about something like carbon dioxide or water vapor, scientists can look at just the light that's given off by a star or light that is reflected by a planet, and that light is going to tell us the chemical composition of that substance. So that's in short how that works. We're going to come back next time and talk about different kinds of these spectra. See you then.